Hello to everyone and welcome to today's webinar. My name is Tanner Swift and I'll be your moderator for this session. I'm pleased to introduce today's speaker, Alex Kirichenko, but before I hand the mic over to our presenter, I do have a few housekeeping items to cover about this presentation. Today's webinar will be recorded and made available on demand after the live session. We will provide you with some of those details later on. We'd love to hear from you during today's presentation. During the session, if you are here on WebEx with us and have any questions for our presenter, please submit those using the Q&A panel where our wonderful panelists are ready to respond. We will also have a couple poll questions for you to participate in today via Slido, so be on the lookout for those during today's session. We appreciate your responses. If you experience any audio issues during today's session, please use the call-in number displayed on the chat screen. I will post that again momentarily. So without further ado, I'd like to kick things off by welcoming Alex. Alex, right over to you.
Thank you, Tanner. My name is Alex Kirichenko, and I'm Solution Architect in Cisco Customer Success. And today we will see the reasons on why to deploy a Service 6. And the main reason is Service 6 simplicity. As we have just for now to talk about all these simple Service 6 things, let's start. In today's session, we will cover a Service 6 vision, fundamentals, introduction to a Service 6 microseat, and demo part. And we start with a Service 6 vision. So this is how current network looks like. So this is very typical service provider. Network service providers are currently having the core domain, which is traditionally layer 3 VPN running over MPLS. And pretty much every service provider has the access domain, or they have maybe a layer 2 VPN, maybe a layer 3 VPN, and typically different technologies. Let's take L2 VPN, where everything is going towards a certain aggregation. And then obviously there is a data center. And the typical technology today in a data center is VXLAN. And this means for every service provider that every service coming into the data center through the packet core must be built in 3 different domains. On top of that, we have to do different technology stitching, like shift-away headend, layer 2 VPN to L3 VPN to VXLAN. So what do we want to do about it? And the main objective of segment routing technology is simplification. Make it simpler. Simply in terms of building services, troubleshooting, maintaining. So what are we proposing? We are proposing one single technology, segment routing, all the way from the access router located anywhere to the data center. And on top of that, running layer 2, layer 3 services, typically based on BGP end-to-end. The service should be simple to build, simple to use, troubleshoot, and understand. And this is what segment routing about. But with segment routing v6, we want to go even further. We want to build service all the way end-to-end. And with the Service 6, it is possible because now we can run a Service 6 on a host. Let's have a look now at the Service 6 fundamentals. What is segment routing? It is an architecture leveraging the source routing paradigm, delivering a unified end-to-end policy-aware network infrastructure over a stateless IP fabric. Segment routing uses the source routing paradigm. An ingress node steers a packet through an ordered list of instructions, called segments. Each one of these instructions represents a function to be called at a specific location in the network. A function is locally defined on the node where it is executed and may range from simply moving forward in the segment list to any complex user-defined behavior. The SRv6 network programming framework combines SR functions, both simple and complex, to achieve a networking objective that goes beyond simple packet routing. The source node chooses the path through the network and encodes that path in the packet header as an ordered list of segments. Each segment is an identifier or an instruction that can be either a topological forwarding instruction or a service instruction. As the other nodes simply execute the encoded instruction without maintaining any per flow state, the network is stateless, making segment routing a highly scalable solution. Here we have one segment, one instruction, reach the destination using the shortest path. Here we can see a similar example, but now we engineer a different path compared to the previous slide. The nodes simply execute the encoded instructions, steering our packet over a desired path. Segment routing applies to IPv6 data plane with a native IPv6 extension. This is achieved through the implementation of routing header called segment routing header, or SRH. Within this framework, the source routed path is encoded as an ordered list of segments, providing a clear and precise routing direction. So when a packet or frame arrives at the source node, it is encapsulated within the outer IPv6 header. This encapsulation may also be accompanied by optional SRH, depending on the network or SLA requirements, and thus ensuring optimal routing efficiency and accuracy. And when a packet needs to follow a specific path through the network, we add a segment routing header. And it might be not needed. And this SRH tells the packet where to go next. The packet's active segment, which is kind of like its next hop, is put into a destination address of the outer IPv6 header. This SRH carries a list of these stops or segment ID that the packet will visit along the way, making sure it follows the path we set for it. The segment is often abbreviated as SID, or segment ID. SRv6 segments have the same format as IPv6 addresses, but they are not IPv6 addresses. The locator part of the segment is formed by the most significant bits and takes the form of IPv6 prefix with a map. It is used to reach the parent node, so it has to be routable. The function is found at the least significant bits of the segment and presents the action to be executed by the node. The function has the local meaning to the parent node, and the rest of the nodes in the topology are not expected to know how interpreted. And the length of locator and function is not fixed, so you can freely allocate the ranges that work best for you. They just have to, in sum, be less than 128 bits. And further, segment locator is subdivided in two portions: seed locator block and seed locator node. And locator leads traffic to the endpoint node, which instantiate the seed and provide the context for the execution of the function. Function represents an opaque identification of the local behavior bound to the seed, and it identifies the action to be performed by the end node. In the context of the given locator, it can represent any action, topological, service-based, or user-defined. Additionally, we could use some of the 128 bits to parse arguments to the node executing the function. And this is not the same as the metadata TLV. It is an alternative to provide some additional information associated to the function. that the node owning the segment can interpret and use. Argument carries optional information required by an SRv6 endpoint behavior. So this is the network program expressed as a list of segments. We are going through the list of these segments, and the first segment will get us to a certain node identified here by locator 1. It will apply function 1, then the next segment goes into the destination address, and we are going to the next active segment with locator 2. Next, we get to a device with locator 2 and repeat same set of operations. It will apply function 2. The next segment goes into the destination address, and we are going to the last active segment with locator 3. Active locator 3 will bring us to the final destination where the function 3 will be applied. IPv6 header format is defined in RFC 2460, and the standard IPv6 header doesn't have any fields to potentially encode segments. And that's why the IPv6 segment routing extension header was defined in the RFC 8754. So this range is optional. We will only have it if the network program consists of more than a single segment or a single instruction. When we have just one, the segment ID is placed at the destination address field of the IPv6 header, and the SRH would not be needed at all. The SRH is used to express a network program. In this slide, we see the complete SRH at the left side and simplified version at the right-hand side. And let's have a look at some fields in more detail. Next header indicates the protocol which is encapsulated in the IPv6 packet. This could be IPv4, IPv6, UDP, or SPL, whatever. We can encapsulate anything because we can transport any type of traffic inside the packet. And if it is 43, what comes after is the routing extension header. And routing type would be 4 for SRH. So at the top, we have the usual IPv6 header, where the destination address will always contain the active segment and will be updated after every instruction gets executed. The tag field can be useful to identify packet sharing in the same set of properties, for example, to apply policies. And if it's not used, it would be set to 0. Segment left is a pointer to the active segment. So together with the segment list, it tells us which instructions come next in the network program. And it is decremented after each instruction is executed. Then we have the list of instructions. The segment list contains the list of segment identifiers in reverse order. This means the first instruction in the program will be the last element in the list. And this is where segment left plays a role in finding the active segment. For example, if we had 3 segments in our network program, we'd start with value SL equals to 2. And we would look at the last segment in the seed list. After executing that instruction, SL would be decremented, taking the value of 1 and so on. An important detail is that the active segment ID is always copied to the destination address field of the IPv6 header. So this is how packets find their way to the node executing the function. At the bottom, we have metadata TLV, and this piece is optional and typically is not used by forwarding platforms like router. Here you could potentially find user information, credential, performance data, or any additional data an application would need to process in order to execute an instruction. And with that, I'm introducing you now to microseed concept, which is a fundamental to the modern Service 6 network. Let's have a look at packet journey for a Service 6 domain with the full length seed. So this is not microseed, this is still full length seed. And let's say Node 6 advertises this FCBB BB00000 0006 E001 seed for some service, 2 VPN or 3 VPN service, for example. And there are some SLAs or policy we'd like to provide for this packet. And it has to go through nodes 2, 3, and 4. So source node A creates a seed list with that prefix being the first seed or first instruction. And it places it with index 0. And then it put other seeds in order for the execution. Segment left would points to 3. So this is the last instruction in the list. And that instruction is copied into the destination address field. And this is how we will see this packet out of the node A. When packet arrives at node 2, it will see its address in the destination and the function to execute. That would be a local function, meaning, for example, adjacency seed to send the packet further out of specific interface. Router 2 would also see that there is a SRH, so it needs to decrement segment left by 1. It would become 2, and copy that new seed into the destination address field. Same on node 3. Update the cell, segment left, update destination address, and forward the packet further. Node 4 would do the same, but after another segment left decrement, segment left would become 0. So all seeds from the list were used, and we can do PSP, or penultimate segment pop. So we remove the SRH and send the packet out without SRH. The segment format in SRV6 has a locator and a function. The locator can be any size, and in this example, it is 64 bits. Then there is a function, and that function says what the device is supposed to do with the packet. We know that function is going to have the function itself and some argument. In real-life scenario, if router wants to send the packet through several devices, through 4 devices, it needs to build a SRH. And then the SRH header has additional 8 bytes and 16 bytes per each individual seed. So router needs to build quite large piece of data, and it needs to put it into the header. We can see here a lot of those data are redundant. The prefix of the network is the same, and there is a router ID, and the router ID must be part of the locator. And the locator is used for the routing to make sure the packet will get all the way there. And each router in the network have different router IDs and the number of functions. And here we have possibilities 2 to power 64, which is a lot. As in reality, we are using just few numbers, and it doesn't make sense now to have so many functions on a single device. So we saw at the beginning, the prefix itself is redundant, it is the same. The trailer of each prefix is redundant, it is always 0. And the building of such packet is quite difficult and has disadvantages. It increases the packet MTU, and it is difficult for hardware to process. So on the Y side, we have a very nice technology, which is a Service 6. And on another side, it's difficult for the current hardware to do such routing and forward. Let's have a look at microseed format now. So microseed container is a 120-bit SRV seed containing a sequence of microseeds. It can be encoded in destination address field of IPv6 header or at any position in the segment list. Microseed container consists locator block, locator node, function, and argument. And it has flexible bit length format, which must be less or equal 128 bits. Locator typically takes care of transporting the packet up to the endpoint node where the segment is instantiated and provides the context for the execution of the function. Function represents an opaque identification of the local behavior bound to that seed, so also known as the service behavior. It identifies the action to be performed by the endpoint node. An argument carries the remaining microseeds. Now, how does this work? We want to preserve all the benefits, all the values of the services. We want to make sure we can send a packet through routers which do not understand the services. And we still want to use some legacy hardware, which is capable of doing just plain IPv6 routing. And one more thing, which is very important for our network, is the network summarization. We want to preserve the SRv6 summarization possibility. So what is the SRv6 microseed? It is just a portion of certain amount of bits which are together 16 bits here in this example. And for our illustration, we use the 16 bits microseed. And another thing to consider, it is about our implementation, and in our implementation, it is 16 bits and 16 bits only. Next, we have a SRv6 microseed locator block, and the block is the part of the addressing space. Here it is 32 bits. So we have a SRv6 block and microseed. Each microseed represents one single device. At the end of the microseed is the end of carrier, or AOC, which is 0. All this is called a SRv6 microseed carrier. It is still 128 bits, like IPv6 address, and this time it is not a seed, but rather a SRv6 microseed carrier. And once we perform forwarding, we can do the same things we did in a SRv6, placing the whole carrier into the destination address and also placing different microseeds. Here we can see an example of microseed. So microseed container with 120-bit SRv6 seed. So we have 32-bit locator block, it's CBB, BB00/32 in this example, and a list of 16 bits microseeds. This slide shows 6-way microseed source routed path with a single microseed container. We can see the entire path is fed into 128 bits and no storage is required. A compressed SRv6 segment list encoding can optimize the packet header length by avoiding the repetition of the locator block and trailing. Here we compress a list with 4 segments into a single carrier. Here on the left side, we see uncompressed segment list with SRH, and on the right side, compressed segment list encoding. So a segment list encoding that reduces the packet header length thanks to one or more microseed sequences. Let's have a look at microseed processing and forwarding. So the source needs to build a packet with a common prefix, and because all those routers have first 32 identical bits, it is FCBB, BB00 for every router in this network. And then it will put the microseed into the carrier. So it will put 2 at the first place, 3 at the second place, and 4 at the third place. In this IPv6 network, everyone knows how to reach FCBB, BB00, 0002. Everyone will make sure the packet gets delivered to the router 2 first. Router 2 will get the packet with the destination address, which is 0002, and as it supports microseeds, it knows what to do with that packet. So right now, there is no segment left pointer. It doesn't exist because there is no storage header. What router 2 has to do is shift and forward. It will shift the remainder of the carrier by 16 bits to the left. It will take everything beyond the prefix and move it by 16 bits to the left, because 16 bits is the size of microseed. So from the destination address, the microseed of 0002 will disappear. And the new destination address is going to be FCBB BB00 003 004. The packet has the new destination address, and R2 will just look up for the new address, for the new destination address in its routing table. And that would be FCBB BB00 003 with mask 48 bits. And it will forward it accordingly to the forwarding table. And please note that between our router 2 and router 3, there might be some other routers that perform just IPv6 forwarding without processing microseed. And when the packet reaches R3, it will do the same things, shift and forward. A legacy node is the one which understands IPv6 but doesn't understand SRv6. The forwarding is based on the IPv6 header and IPv6 forwarding rules. So when a legacy router, which is not SRv6 capable, receives an IPv6 packet, it performs the longest prefix match lookup on this packet's destination address. So let's go now through this packet journey using microseed when SRH is needed. The ingress router will put the carriers into the packet. It will do encapsulation reduce, and it will put one single carrier directly into the destination address. And the second carrier is put into SRH. Legacy nodes do not perform any manipulation with the header and simply forward it further based on the IPv6 routing entries. Once the packet reaches R2, it will do shift and forward. Now the next destination address is the router 3, and nothing else has changed. The packet reaches R3, it will do exactly the same, shift and forward. The next destination address is for the router 4. The same on R4, shift and forward. And yes, so we're adding zeros at the end for carrier indication. R5 is the same, shift and forward. The same is on R6, shift and forward. And now the packet reaches R7. R7 will see its microseed, and there is the end of the carrier. Now that this is over, this packet is either for router 7 or maybe there is an SRH. And yes, indeed, there is an SRH. And we need to do the lookup into the SRH for an additional segment. And it will do the end function of a service 6, decrementing segment left and copy the new carrier into the destination address. As segment left becomes 0, we can get rid of SRH and do penultimate segment pop. So next header would be changed as well. And in this example, it would be IPv4. And then R7 will forward it further. We have a very rich ecosystem, and this was our commitment to delete operators. And I'll let you look at this slide for a few seconds, but we have everybody here. And all these vendors are part of the microseed solution. So let's move to the demo part now. And in this demo today, I will demonstrate the Service 6 initial configuration and slicing example with the Service 6. So this is the topology we have now, and all the routers are already enabled and configured with Service 6, except router 5 and router 6. So we are going to do the initial configuration on these two routers and see how it goes. And this is the configuration context. This is ISIS net address, which we would use to configure these two routers. Microseed block is FCBBBB00, and we will use router ID for the locator. We have router 5, we have router 6, and let's begin with configuring a loopback address on router 5. So we see we have locator block, and we assign microseed to the locator. Emit configuration, show IP6 interface loopback 0. So we can see loopback IPv6 is enabled, and we have our address assigned. Let's go to interface 000 facing R6 and enable it. And we use link local addresses, so we don't assign any explicit IPv6 address here. So now let's enable ISIS on router 5, placing these two interfaces there. So there is no segment router yet. Segment routing, so we assign net address, we enable ISIS on loopback 0 and the gigabit 00 interface. Next, we configure first locator on our router 5. So let me show it to you. So this is locator, and we put the name main. So this is locator itself. So we use the same locator block and then router ID. And this, we said that it would be microseed behavior. Let's have a look at the Service 6 manager. Now we commit the configuration. To segment routing, Service 6 manager. So what we see, Service 6 is enabled and operational. We can see seed block. We can see the format 3216. Scrolling down, we can see some summary of use locator and resources utilization. And then at the further down in the output, we see platform capability. So we can see what is supported by every router. And here we can see it supports the service 6, TLFI, micro loop avoidance, and different endpoint behavior are also listed here. So now we have configured ISIS, we configured locator, but now we want to add this locator into ISIS, so it will be advertised. This is how we do it. On the router ISIS configuration, we specify our locator we just configured. And let's have a look at the locator, show segment routing, service 6 locator main. So we can see this is locator and it is up right now. Let's quickly do the same on router 6. So we configure loopback address. Now you can see it uses the same locator block, but now the locator is 6 for router 6. We enable ISIS into interfaces, loopback 0 and gigabit 00. So you see the configuration is the same. Net addresses for router 6. We enable loopback 0. We enable gigabit 0. Next step, we configure locator on the router 6. So again, you see the configuration is the same. It's just the prefix is for router 6. We add the locator under the ISIS router. So we can advertise it, emit the configuration. And what we need to enable the interface 0 facing the router 5. We commit the configuration, show ISIS neighbor. We can see our neighbor as router 5. Let's look at the segment IDs. So segment routing, service 6 seed all. So we can see seed for the node, and we can see seed for adjacency. It got automatically allocated when we configure segment routing for ISIS interface. Now let's have a look at the routing table and go through a few examples. So we have show route IPv6. And what we see here, for example, for endpoint node behavior, we can see two prefixes. One is with mask 64 and one is with mask 48. So if we match 64, that means there are zeros behind the 6. So that means we are matching end of carrier with this prefix. And if this is the end of carrier, then we do PSP or USD behavior. If otherwise we match 48 mask, that means there are some other microseeds behind it. And if that's so, then we do shift and forward behavior. Let's have a look now at the ISIS database. ISIS database, and we do it for our router 6. So we can see now we advertise a service 6 locator, and this is our locator, and this is again the seed. And going down the output, we can see we advertise adjacency seed as well for our gigabit 000 interface. And we can see again our locator, but now it is advertised as prefix and not as a locator. And we do it for backward compatibility with nodes which do not support SRv6, but support IPv6. So all other nodes which just support IPv6, they install this prefix into their routing table, and they would know how to reach this router 6. Okay, now let's quickly enable interfaces 2 and 4 on both devices and connect these two routers to the rest of the network. So we just enable these two interfaces. And what we have here, we can see we've got all the prefixes there. So that was the initial configuration on how to enable SRv6 on the router. And now let's quickly do slicing configuration. So we will use Flex Algo for the slicing demonstration. And this would be our network. And this time we will use slice, which is based on the delay. So we want to build a network which knows the delays in the between every router and use the path with the shortest delay. In this virtual environment, we don't have dynamic measurements, so we put static measurements on all the links between the routers, and you can see these measurements on the topology. Now let's add the new locator for this slice, and we start with router 6. So you can see we configure locator, we name it latency. We again use router 6 and we allocate different locator 08. And we assign algorithm to 08 for it. So we commit the configuration. If we look at the segment routing configuration now, you can see we have two locators. One locator, which is BB00, and new locator BB08 for the new algorithm. Now we need to add this locator into ISIS for advertisement. And we also want to specify that this algorithm would be based on the delay now. So that would be the configuration. We add second locator, and we say that this Flex Algo 208, which we just configured, would be based on the delay. So let's have a look at the complete configuration. You can see now we advertise two locators and locator specification. So let's have a look at this new algorithm. Show ISIX Flex Algo 208. And you can see now it is based on a delay. And the rest of the network is already enabled. So what we do, show SIS, IPv6, route, flex, algo 208, and we can see all the routers which participate in this algorithm advertise the prefixes. And we don't see our router 5 because router 5 was not configured. Let's enable the locator on router 5. And now if we look again, we've got our router 5 here. So how can we use it now? So we have a second slice with different locator, which is based on delay. Let's have a look at the classical AGP routing, which is based on the shortest AGP method. And we look how we would reach the router 5 with the original locator. And it was FCBB, BB. So it's 0, 0, our original locator with original AGP configuration. So this is the locator, and we can see we reached our router 5 through gigabit 00, which is expected. That was the shortest path with our original locator. Now let's check how we would reach the router 5 using the new slice and new locator. And you can see now we have a CMP path through interfaces 2 and 4. And this is metric. And you can see that using different slides, we change the network behavior, and we are providing different SLAs now. And by just using different destination IP address, we can use different slides now with the service 6. And what we can do as next demonstration, let's, for example, ping the router 7. Okay, it is pingable. Let's do trace route. Trace route, you can see the path, how it goes through the network. Okay, let's do. And yes, by the way, the locators are pingable. So we can remove the one which belongs to the loopback address, and we can just ping or the trace route using the locator to check if it's properly configured. But now, for example, this is ping using classical network-based behavior. And what we can do now, we can add our own SRH using this command via service6 carrier, and we add carrier into our packet. So it's BB, BB00. And let's say we want to send our packet, so it's from router 6. We want to send it to 3 first, then we want to send it to 4, next to 2, and next to 1. Let's say like this. Just count 1. Okay, and we can do the same with trace route. Just to confirm the behavior, trace route, probe 1. And we can see the replies. So first it goes from router 3, and this is our destination address. Because as you can see, we are pinging 107, and 107 now will be at the end of the list. So 107 goes to SRH, and carrier, the first carrier goes to the destination address instead. And we can see with every router, we are removing microseed from a destination address. But we can go even further. Let's say our packet loves to stay in the network, and we can add another carrier. We can say we want to do FCBB, BB00, and then we go 5, 6, 3, 4, 2, like this. And now you can see we have 2 carriers, and the packet goes all the way we programmed it to go. And let's try to capture this packet. So it's from router 7, and we have Wireshark running on this interface. Let's run it here. And let's do probe count 1. Ping count 1. And here we have our packet captured. This is a CMP, so we can see our source, address 6, our destination, the carrier one, and we can see the SRH. So at the index 0, we have our final destination, which is router 7. Then we have second carrier we programmed, and then we have our first carrier, which goes into the destination address. And this is all I wanted to show you today. And Tanner, back to you.
Alex, thank you so much. Great job, and always appreciate having demos up here for our attendees anytime that we can give them. Just as a reminder to everybody, those polling questions are now live via the Slido link. You can use the Slido panel here in WebEx, or the direct link is in the chat for you as well. We have reached our Q&A portion of this session. So just as a quick reminder, if you do have a question for Alex or our panelists, please submit those using the Q&A panel on WebEx, and we will respond to them here. I've had a few questions that come through that have been answered, but I wanted to get to a couple questions here. Alex, I'll start with you. We don't use segment routing at all, neither SR-MPLS or SR-V6. Do you recommend moving to SR-MPLS first and then moving to SR-V6?
The decision to move to service 6 should be evaluated based on your specific needs and constraints in your network. So both service 6 and SR-MPLS, they have their different cons. Either of them can be right choice for you, depending on the use case. But moving directly to service 6 can offer you several advantages over SR-MPLS, like simplified network architecture, greater flexibility, integration with IPv6, or services integration.
Perfect, thank you. Let's go on to the next one. How does legacy IPv6 node know what to do with the SR-V6 address locator?
So it will treat the service 6 locator just like a normal IPv6 address. As we saw earlier, a legacy IPv6 only nodes, they are unaware of service 6 encapsulation, and they only would look at the outer IPv6 header for routing decisions, so they won't look down further. And this is why service 6 nodes advertise locator as locator in IFS LSP, and it also advertises it as a prefix for backward compatibility for IPv6 nodes only.
Great, and a follow-up question off that, can server 6 be deployed in a network where the IPv6 is not deployed end-to-end?
Oh yes, definitely, because you can run in parallel IPv4, IPv6, and we also support service 6 and MPLS internet networking. So that's definitely possible.
Great, thank you. Wanted to, here's a question that just came through from E1. Just asked if you don't mind touching a bit on the G-SRv6 in comparison to the USID.
Sorry, compare SRv6 to... Sorry, can you repeat the question?
Yeah, sorry. Touch a bit on G-server 6 in comparison to the USID.
G-server 6. I think I'm not getting what is G-. we have it. It should be G, S, or V.
I know that's actually the standard that is proposed by Huawei. Right now, there are a bunch of works happening between Cisco and Huawei to come to a USID type of implementation. So both of them are focusing on reducing the header size, because when we're looking at the SRv6, if we put quite a lot of fields, we're increasing the header type, the header size quite a lot, and that is reducing actually the potential of sending a lot of traffic on the wire.
Thanks for jumping in on that one. Really appreciate it. And Jan just gave a good link response as well. Another question here from Billy. Are there any useful features within Catalyst Center that help with a Catalyst Server 6 network?
I don't know anything about Catalyst Center, sorry.
No, okay.
I'll pick it up. So Catalyst Center is focusing more on deploying SDA, which is based on Lisp and VXLAN. Practically, Catalyst Center is not really focusing on SRv6. What we can do is, for example, run to the edge, and after that have a termination of the SRv6 service into a VLAN connecting to the campus. Where the SRv6 is connecting very well is in the data center. So practically on the NXRS, we can run end-to-end from the last host till the last user that is running the IPv6, we can run the top.
Perfect. Thanks for jumping in on that. Really appreciate it. We are winding down here for the live session. We are going to keep the Q&A window open for just a couple more moments, just in case you do have any questions. We'll be able to type those out and in response. But Alex, want to give you the stage just here for one more minute. Is there anything else that you would like to cover before we wrap up?
If you plan to move to segment routing, consider Service 6 because it's definitely simpler to use compared even to SRMPLS because you get rid of multiple protocols, LDP, RSVP, BGP, LU. So it's easy to configure, as you have seen it, and then easier to troubleshoot and maintain. And when the session will be closed, you'll get a survey question. And if the session was interested for you, there would be a question if you would like to see continuation of the services presentation. And then we can continue and give you more details and more things on the services.
Alex, really appreciate it today. I want to thank all of our panelists and the whole team for bringing your knowledge to the Cisco community today. As I just mentioned, if you do have a question, we'll keep that Q&A window open for a couple more minutes. For even more tutorials, demonstrations, and future webinars, please visit the Cisco Learning Network. I'll place a link in the chat screen for that momentarily. It usually takes about 5 business days for today's session to be uploaded to our learning plan on the Cisco Learning Network. However, with today's YouTube live stream, you'll be able to check the playback at any time. I'll also provide a link here in the chat screen where those recordings will be linked, as well as a post-webinar discussion thread on the Cisco Learning Network where you can ask any follow-up questions about today's session. Your feedback is important, and at this time, you'll be directed to a post-webinar survey. Please take the time to participate in that. It helps us plan out future sessions. Once again, we thank everybody for joining us today, and we will see you next time on the Cisco Learning Network.